Hey everybody, Tanya Peel here with Respiratory HQ. Yesterday on Instagram and Facebook, I posted the HQ challenge. So today I just wanted to come back and I wanted to use this as an opportunity, number one, to give you the answers, but work through this from a test taking perspective, okay? So this is how we started out. Which of the following would the RT expect to find on a patient diagnosed with atelectasis? So which would you expect to find? So an increased alveolar oxygen tension, a decreased O2 saturation, a decreased hemoglobin, or an increased temperature. Okay. So I want to start this from the opportunity of maybe weeding things out, things that we absolutely know is not going to be the case. So this is atelectasis, right? So let's just make sure we're understanding. So instead of a nice fully inflated alveoli, we have a section of the lung, or maybe a large section of the lung, those alveoli may be completely collapsed, or maybe they're just not fully expanded. But basically, we've lost surface area for oxygen to diffuse across into the capillary bed. So let's just start and weed out, knowing this is what we're dealing with. Let's weed out some things. So let's start with hemoglobin. Atelectasis and what's going on in the alveoli does not change the amount of hemoglobin that is in the bloodstream. It really has no impact on the amount of hemoglobin in the body. So let's get rid of that. That is not going to be an option. Whoops, that's not going to be an option. Okay. An increase in temperature. Well, atelectasis is not an infective process or an infectious process like pneumonia. So one of the differentiating diagnosis between atelectasis and pneumonia is the presence of a fever. And so with atelectasis, a person's going to be afebrile. They won't have a fever more than likely. So they're not going to have an increased temperature, because that just doesn't have anything to do with it. So already we've narrowed things down to two options. All right, so let's deal with this, an increase in the alveolar oxygen content. So let's make sure we know the formula. Again, we're dealing with an atelectatic region of the lung. Here's the alveolar air equation: barometric pressure minus water vapor pressure times the FiO2 minus the CO2 times 1.25. Now, this is where math comes in handy, or at least understanding the formula. So the portions of the formula that create the alveolar oxygen pressure have to change in order for the P big AO2 to change. So nothing in our setup tells us the barometric pressure is different. Water vapor pressure is always going to be 47. The FiO2 hasn't changed, and we know nothing about the CO2. So atelectasis in and of itself doesn't change the components of this mathematical formula for alveolar oxygen tension. Basically, it doesn't even have anything to do with it. So that P big AO2 is not even an option here. So what the answer has to be then is a decrease in saturation, and that is absolutely right. Whatever oxygen is calculated to be in the lung, and this is an overall lung calculation for P big AO2, that oxygen is driven into the pulmonary capillary bed. But when we have a section of the lung that is either collapsed or not fully expanded, we don't have surface area then for oxygen to diffuse into the AC membrane. So the amount of oxygen in these atelectatic areas, our hemoglobin, while it may be normal, our saturations will be lower. So we'll have a lower SaO2 and more than likely a lower PaO2. So that's why when you're looking at this situation, okay, they're going to have a decreased SAT. Okay? So that's the first question. The second question was, if this patient's SaO2 is 90, okay, assuming they have atelectasis, you draw a blood gas and their SATs on their blood gas are 90%, what is the approximate PaO2? And if you watch the video on YouTube, there is that relationship between saturation and PaO2, and that ties into this oxygen hemoglobin dissociation curve. So if we look and say, okay, here's the saturations, here's the P little AO2. If our saturations are 90 and you travel that across to where it comes in contact with the curve, and you draw a line straight down, that tells us that the P little AO2 is about 60. Okay? And then the third question asks, what is the primary? That's the key word. The primary reason the CaO2 is decreased, so this is oxygen content. The main reason oxygen content is decreased. And so let's go back to this right here. This is the formula for oxygen content. So hemoglobin times saturation times 1.34 plus the P little AO2 times 0.003. This is oxygen content. And so we just said that the sats are low and the P little AO2 is low. And if you've watched the YouTube video, the main way oxygen is transported in the blood is through hemoglobin. So now, knowing that, and we go to what is the primary reason the CaO2 is low. Well, it's not anything to do with the A to A difference. We're not talking about that. We're not talking about ventilation, because ventilation, it has to do with CO2 removal and pH. We're not talking about that. So now it leaves us with the amount of oxygen dissolved in the plasma is low. Well, that is a true statement. Or the amount of oxygen bound to the hemoglobin is low. Well, that's a true statement also. But we go back, what is the primary reason? The main way oxygen is transported in the body is bound to hemoglobin. So this person's O2 content is low because of that low saturation, what is bound to the hemoglobin. I hope you found this helpful and hope to see you soon.